In the world of statistics, we often obsess over averages, the mean performance. But there's a silent hero, or villain, that determines the reliability of our data: variance. Welcome to the F-Test, comparing variances without getting a headache. Today, we'll see why knowing how much your data spreads is just as important as knowing where it centers. Imagine two archers, Alice and Bob. Alice hits the bullseye occasionally, but her shots are scattered all over the target. Bob never hits the exact center, but all his arrows are bunched tightly in a small circle. Who is more consistent? Bob, of course. In statistics, this tightness or spread is what we call variance. The F-test is the mathematical tool we use to prove if the difference in consistency between two groups is statistically significant or just a result of random luck. The heart of this test is the F-statistic. The formula is deceptively simple. F equals S1 squared divided by S2 squared. Here, S squared represents the sample variance. By convention, we usually put the larger variance on top so that F is always greater than or equal to 1. If the variances are identical, F equals 1. The further F moves away from 1, the more evidence we have that the two groups are fundamentally different in their stability. But we can't just look at the number. We need context, and that context comes from degrees of freedom, denoted as df. Since we are comparing two samples, we have two sets of degrees of freedom, one for the numerator and one for the denominator. Calculated as n-1 for each group, these values shape the F distribution, a skewed curve that starts at 0 and stretches toward infinity, never going negative because variances are squared. Unlike the familiar bell-shaped normal distribution, the F distribution is non-symmetric. Its shape changes drastically depending on your degrees of freedom. When we perform the test, we look for a critical value based on our chosen alpha level, usually 0.05. If our calculated F-statistic lands in the rejection region at the far right tail of the curve, we reject the null hypothesis. We conclude that the variances are truly different. Let's look at a real-world scenario. A pharmaceutical company is testing two different machines that fill medicine vials. Machine A has a variance of 0.04 milligrams, while machine B has a variance of 0.09 milligrams. Is machine A significantly more precise, or is the 0.05 difference just noise? By calculating the F ratio, 0.09 divided by 0.04 equals 2.25, and checking it against the F distribution for their sample sizes, the company can make a data-driven decision on which machine to keep. In summary, the F-test is your go-to tool whenever consistency matters. Whether you're checking if two investment portfolios have different risk profiles or ensuring manufacturing quality across different plants, the F-test provides the rigor needed to compare variability. Remember, the mean tells you where you are, but the variance tells you if you can trust being there. Thanks for watching.